This lecture is about the syntagmatic relation discovery and entropy. In this lecture, we're going to continue talking about word association mining. In particular, we're going to talk about how to discover syntagmatic relations. And we're going to start with the introduction of entropy, which is the basis for designing some measures for discovering such relations. By definition, syntagmatic relations hold between words that have correlated co-occurrences. That means when we see one word occurs in the context, we tend to see the occurrence of the other word. So take a more specific example here. We can ask the question, whenever eats occurs, what other words also tend to occur? Now, looking at the sentences on the left, we see some words that might occur together with eats, like a cat, dog, or fish, these, right? But if I take them out, and if you look at the right side, where we only show eats and some other words, the question then is, can you predict what other words occur to the left or to the right? Right? So this would force us to think about what other words are associated with eats. If they are associated with eats, they tend to occur in the context of eats. So more specifically, our prediction problem is to take any text segment, which can be a sentence, a paragraph, or a document, and then ask the question, is a particular word present or absent in this segment? Right here, we can ask the question about the word W. Is W present or absent in this segment? Now, what's interesting is that some words are actually easier to predict than other words. If you take a look at the three words shown here, meat, the, and unicorn, which one do you think is easier to predict? Now, if you think about it for a moment, you might conclude that the is easier to predict because it tends to occur everywhere, so I can just say, well, the will be in this sentence. Unicorn is also relatively easy because unicorn is rare, it's very rare, and I can bet that it doesn't occur in this sentence. But meat is somewhere in between in terms of frequency, and it makes it hard to predict because it's possible that it occurs in the sentence or the segment more accurately, but it may also not occur in the segment. So now let's study this problem more formally. Right? So the problem can be formally defined as predicting the value of a binary random variable. Here we denote it by x sub w. W denotes a word, so this random variable is associated with precisely one word. When the value of the variable is 1, it means this word is present. When it's 0, it means the word is absent. And naturally, the probabilities for 1 and 0 should sum to 1 because a word is either present or absent in the segment. There's no other choice. Okay. So the intuition we discussed earlier can be formally stated as follows. The more random this random variable is, the more difficult the prediction would be. Now the question is, how does one quantitatively measure the randomness of a random variable like x sub w? How in general can we quantify the randomness of a variable? And that's why we need a measure called entropy. And this is a measure introduced in information theory to measure the randomness of x. There is also some connection with the information here, but that's beyond the scope of this course. So for our purpose, we just treat entropy function as a function defined on a random variable. In this case, it's a binary random variable, although the definition can be easily generalized for a random variable with multiple values. Now, the function form looks like this. There's a sum of all the possible values for this random variable. Inside the sum, for each value, we have a product of the probability that the random variable equals this value and the log of this probability. And note that there's also a negative sign there. Now, entropy in general is non-negative, and that can be mathematically proved. So if we expand this sum we'll see the equation looks like the second one, where I explicitly plugged in the two values, 0 and 1. And sometimes when we have 0 log of 0, we would generally define that as 0, because log of 0 is undefined. So this is the entropy function. And this function would give a different value for different distributions of this random variable. And it clearly depends on the probability that the random variable taking a value of 1 or 0. If we plot this function against the probability that the random variable is equal to 1, and then the function looks like this. At the two ends, that means when the probability of x equals 1 is very small or very large, then the entropy function has a low value. When it's 0.5 in the middle, then it reaches the maximum. Now, if we plot the function against the probability that the x is taking a value of 0, and the function would show exactly the same curve here. And you can imagine why. And so that's because the two probabilities are symmetric and completely symmetric. So an interesting question you could think about in general here is, for what kind of x does the entropy reach maximum or minimum? And we can in particular think about some special cases. For example, in one case we might have a random variable that always takes the value of 1. The probability is 1. Or there's a random variable that is equal likely taking a value of 1 or 0. So in this case, the probability that x equals 1 is 0.5. Now, which one has a higher entropy? Now, it's easier to look at the problem by thinking of a simple example using coin tossing. So when we think about the random experiment like tossing a coin, it gives us a random variable that can represent the result. It can be head or tail. So we can define a random variable x sub coin so that it's 1 when the coin shows up as head. It's 0 when the coin shows up as tail. So now we can compute the entropy of this random variable. And this entropy indicates how difficult it is to predict the outcome of a coin tossing. So we can think about the two cases. One is a fair coin. It's completely fair. The coin shows up as head or tail equally likely. So the two probabilities would be a half, right? So both will have both are equal to 1/2. Another extreme case is completely biased coin, where the coin always shows up as head. So it's a completely biased coin. Now let's think about the entropies in the two cases. And if you plug in these values, you can see the entropies would be as follows. For a fair coin, we see the entropy reaches its maximum, that's 1. For the completely biased coin, we see it's 0. And that intuitively makes a lot of sense, because a fair coin is most difficult to predict. Whereas a completely biased coin is very easy to predict. We can always say, well, it's a head, because it is a head all the time. So they can be shown on the curve as follows. Right? So the fair coin corresponds to the middle point, where it's very uncertain. The completely biased coin corresponds to the end point, where we have a probability of 1.0 and the entropy is 0. So now let's see how we can use entropy for word prediction. Now the problem, let's think about our problem, right? To predict whether W is present or absent in this segment. Again, think about the three words. particularly think about their entropies. Now we can assume high entropy words are harder to predict. And so we now have a quantitative way to tell us which word is harder to predict. Now if you look at the three words meet the unicorn again, and we clearly would expect the meet to have a higher entropy than the or unicorn. In fact, if you look at the entropy of the, it's close to zero because it occurs everywhere, so it's like a completely biased coin. Therefore, the entropy is zero.